Do you get my last day's lecture? I have already put in the Microsoft Teams. Also, you can, if you want, you can listen to the recorded lecture also. Previous day's lecture was also recorded. Okay. If you want, you can listen. Otherwise, if you are in the class, you can understand. So don't have to listen again to the that lecture. Okay, recorded lecture. Now, let me go to my slide. Can you see the slide, PPT?
Yes, ma'am.
Okay. So again, the same reference, environmental chemistry by A.K. Day. And today I will tell about the tropospheric chemistry. Last class I discussed about the ozone layer, which is present in the stratosphere, right? But today I will tell about the troposphere. You know, troposphere where we are living. Okay, it is up to 11 kilometer that I told you that day, na? Uh, what is there in the troposphere? You can see here, and the gases. Okay, so those are like pollutants. SO2, sulfur dioxide, then H2S, carbon monoxide, nitric oxide, nitrogen dioxide, NH3, hydrocarbons, all those things, and even some more are there. And the chemistry of these gases is very important in the troposphere. Okay, there are a lot of oxidizing substances are present in the troposphere, and they can oxidize those gases. Okay, and the chemistry varies. The reactions, they are different in daytime and nighttime. Okay, because in the daytime, you know, there is sunlight and some visible light, as well as some higher range UV light is also coming. So they are responsible for different types of reactions. One such reaction is the formation of hydroxyl free radical, H dot, in daytime. Principal oxidative chemical species in daytime is the hydroxyl free radical. You know, this is a very strong oxidant. Nowadays, we are doing many pollutant degradation reactions by using this reactive species. It is called ROS, reactive oxygen species, ROS. Okay. You know, how can we know the property of a substance, how strong it is, means oxidizing power? Okay, whether it is a very strong oxidant or it is not that strong, how to know? You all know, because you are in the school days you have learned E0 values. From the E0 values you can tell that whether something is very strongly a strong oxidizing agent or not. Okay, so if you compare potassium permanganate, you all know that potassium permanganate is a very strong oxidant, especially in acidic condition, strongly acidic condition. It is a very strong oxidant, and the E0 values, that MnO4 minus Mn2 plus system, the E0 value is 1.5 plus 1.5 volt. Okay, but here if you look into the E0 value of OH dot, you will see that it is much higher. It is around 2.8. Okay, plus 2.8. So you can understand that potassium permanganate, we know, very strong oxidant, but it is even means stronger. Okay, so these free radicals are generated in daytime. Now, these OH dot radicals, they can react with many things to form many compounds. Okay, in spite of the high concentration of dioxin, oxygen is also an oxidant, right? But and concentration of oxygen is also very high in the atmosphere. But most of the oxidations are not carried out by oxygen. Most of the reactions, oxidation reactions, are carried out by this hydroxyl radical. Okay. Now, you know radical. Okay, radicals are very reactive species, right? Now, how first a trace amount. Some gases are produced at very low concentration, and those gases, trace gases, how first they will react with the hydroxyl radical can be a measure of their residence time. If they react fast, then they will not stay for a long period of time, isn't it? And in the atmosphere. But if it is inert towards the oxidation with these radicals, then the residence time will be very high. And what will happen if they do not react in the troposphere? They will go to the stratosphere, isn't it? And stratosphere, you know, ozone layer is there. So they will react with the ozone, and then ozone layer will be depleted. The same is going on with the CFCs. I told you that chlorofluorocarbon that is coming from the refrigerators and different sprays, it is a solvent. So they are responsible for ozone layer depletion. So we are releasing those things, and what they are not reacting in the troposphere. They are quite inert there, and but they, when they go to the stratosphere, then they react. Okay, such is the case of CFCs, N2O, CH4, CH3Cl, all those things. So that is one thing you have to remember, that what is the lifetime, what is the residence time or lifetime for some species. Then according to that you will know that whether they will be reacting faster, or they will be staying there for longer period of time. Accordingly, the composition of the atmosphere will vary. Okay. Now, all the oxides of nitrogen are thermodynamically unstable, okay, with respect to the elements. Nitrogen oxides are unstable. They can decompose into nitrogen oxygen, okay. They accumulate to much higher than the equilibrium concentrations in the atmosphere because their rates of decomposition are slow. They can decompose. Thermodynamically it is possible, but their decomposition rate is slow. You know, something is thermodynamically controlled, something is kinetically controlled, okay. Something which thermodynamically it is not feasible, they will not happen. Even if you give catalyst, or even if you give some proper atmosphere, still it will not happen. So kinetics kinetics will be considered only when some reaction is thermodynamically feasible. Okay, but here when the oxides of nitrogen will be decomposed to nitrogen and oxygen, that is slow. Okay, that reaction is slow. The interconversion between NO, NO2 and N2O4, these are the oxides mainly present in the troposphere. Okay, in the troposphere, they can interconvert. Okay, they can, one oxide can go to another oxide, one form to another form. So it is rapid. Interconversion is rapid, strongly temperature dependent. So in pollution reports, that is why we represent the nitrogen oxides. We do not know how much NO is there, how much NO2 is there, how much N2O4, which is a dimer of NO2, is there. Therefore, we tell total. How will you represent NOx? Same is true for SO, sulfur oxide also, SOx. NOx, SOx. This is a very important term for environmental chemistry or environmental science. Okay. NOx means it may be NO, it may be NO2, it may be N2O4, or it may be a mixture also. Okay. Now, two things you will learn today: photochemical smog and reducing smog. Smog, you know smog, SMOG, smog. Smoke and fog, together it is smog. Okay. But there are different types of smogs. One is the photochemical smog, Another is the reducing smog. And they have very popular name also. Reducing smog is called London smog. London, London smog. And the photochemical smog, it is named as Los Angeles, LA, Los Angeles in US, okay, Los Angeles smog. Because this photochemical smog, why it is named as Los Angeles smog? Because in Los Angeles, this happens usually, most common there, okay. And in London, the reducing smog is common, okay. That is why they are popularly they are known as London smog and photochemical smog. Their property is also different, totally different. Their constituent is also different. And photochemical smog is oxidizing in nature. Okay, it is also called oxidizing smog. And London smog is reducing in nature. Okay, constituents are also different. Now you can see that to form the photochemical smog, 4 things are very important. First is the hydrocarbons. Okay, hydrocarbons should be there. Hydrocarbons should be there. Then bright sunlight should be there. Bright sunlight should be there. Then nitrogen oxides should be there. Okay, NOx should be there. Then ozone should be there. So these are the 4 constituents that should be present to produce the photochemical smog. The color of the photochemical smog is brown. Brown, it is called haze. Brown haze, okay. And the reducing smog is like whitish in color. It is not brown in color. It is whitish in color, and the nature is reducing. Okay. So what is photochemical smog? Before that, going to that, you know this reaction NO2 by the action of light, light, it can give nitric oxide and oxygen. This oxygen means O. This O can react with oxygen, dioxygen, to produce the ozone. Okay. Now this ozone, this is happening in, I have shown you the ozone layer formation and depletion in the stratosphere. But here I am telling about the ozone formation in the troposphere. In the stratosphere, ozone is protecting us from the UV light, okay? But in the troposphere, if ozone is present even at 3 ppm, then it is alarming, okay? Ozone alert is there. Below 3 ppm even the ozone alert is there. So in urban air triggers an ozone alert. You can see so low concentration, okay. And 10 to 15 ppm of ozone concentration is sufficient to kill small mammals. So ozone is very means it has high oxidation power, and it is also very it can kill a person. Okay. In addition, ozone can react with incompletely oxidized organic compounds from gasoline. When we run the vehicle, in the vehicle, what is the fuel? The fuel is gasoline, right? What is gasoline? Gasoline is nothing but the hydrocarbons, okay? So when you run the vehicle, then some amount of gasoline, fuel, is escaping out, okay? So in the atmosphere, okay? So this gasoline can react and it can be responsible for that photochemical smog formation. I will show you how it is occurring. Okay, what are the reactions behind this photochemical smog formation? And there is another thing that it is called pan. Okay, I will show you what is pan. This pan also responsible for the this photochemical smog is very much irritating. If you run your vehicle or if you pass through the photochemical smog, you will feel in the lungs, or you will feel irritation. Okay, and very toxic. Pan is very toxic. how is it irritant, harmful irritant, okay? So how it is formed, that I will tell you, okay? Now, troposphere chemistry, the major source of OH dot radical is ozone photolysis. How OH dot is produced? I told you that OH dot is very strong oxidant. So how OH dot is produced? Ozone, which is present in low concentration, but still it reacts with the UV radiation. You know, very small part of UV radiation penetrating also to us, means it is penetrating through the ozone layer and it is coming to the earth. So that UV light, it is, the lambda is below 320 nanometers, okay? 320 nanometers, you know, from 350 we can tell that it is visible, okay? So, but this light also, this light falls in the UV range, but it is not very low wavelength. So UV light, UV range starts from 200 to and ends at 400, at least 350, but it is very close to 350, okay? Now, ozone when reacts with this UV light, it can form O, and O when reacts with the moisture, water, it is always there in the atmosphere, so it will form the OH dot. At night time, this reaction does not happen because sun is not there, so this reaction does not happen, and at night time this is not the main reactive species, but the nitrate radical acts as the main oxidative chemical species and takes over from OH dot. However, NO3 dot is less reactive than OH dot. It is more reactive. OH dot is more reactive. Okay. NO3 dot is easily photolysed and therefore its daytime concentration is very low. NO3 dot, even if it is produced, but it is photolysed with light, it decomposes. Okay. You know photolysis. Photolysis means, lysis means breaking down. Like hydrolysis, you know, with water something is breaking down. It is hydrolysis. Photolysis, with photon something is breaking down. Thermolysis, with heat something is breaking. So lysis means breaking down. So NO3 dot, even if it is produced in the daytime, it will be photolysed and so concentration will be less. But at night time the concentration is higher. So it is the reactive species. Okay. Now I will show you the how the sulfur oxide, okay? The oxides of sulfur have long been known as serious contributors to air pollution. Their effect is truly global because they have longer lifetime. They can stay for long period of time. So when something is staying for long period of time, they can be carried over by the wind from one place to another place, okay? Before they react, it goes from one place to another place. So it becomes the truly global. The effect is truly global, okay? And it stays for a long period of time. A certain fraction of SO2 and SO3 in the air originates from, where from it is coming? Sulfur oxide, it is a pollutant and it is there always. But how it is produced? Okay, it is produced from there are some sources from biological processes. Okay, under aerobic condition, say for example some organic matter which contains sulfur. Okay, under aerobic condition, when it is decomposed, that organic compound is decomposed, what is the fate of the sulfur? The fate of the sulfur is that because it is in presence of oxygen, so it will form the SO2 or SO3. Okay, this is one process. But maximum amount of SO2 is coming, or SOX, here we should tell SOX is coming from the fuel. Because you know in the coal there is some sulfur, okay? In petroleum there is some sulfur, okay? So when you burn it, what will happen to the sulfur? That sulfur will be oxidized and it will form the SOX. So this is the main source. Okay. Now, then what protection we should take so that the SOX is not produced and it does not come to the atmosphere? What protection we can take? The protection we should take is that we should use a good quality fuel, means which contains less amount of sulfur in it. Okay. Otherwise, when when it is burnt, the coal or petroleum is burnt, the exhaust, the gas which is coming out should we should do something so that from the exhaust gas is the SO2 which is produced, we can take out from that gas. This SO2 reacts either chemically. Oh, this is next part. So this we can take out, or it can be absorbed, or something we have to do, okay, so that it does not come to the atmosphere. Now what happens? What is the fate of this SO2, okay, or SO3? What is happening? It reacts. SO2 reacts in this way, and it forms it reacts with water. It reacts with water. First it reacts with oxygen and then water to form the H2. So because SO2 when reacts with oxygen, it forms SO3, where the oxidation state is +6, right? +6, and in H2SO4 also it is +6. So initial step obviously is the formation of SO3, then in the water it dissolves and it forms the H2SO4. Okay. So this H2SO4, it can form the aerosol. Okay, aerosol. So there are many other reactions, that it can form the reactive radical also. So you can see that this is forming the reducing smog, mainly the sulfur oxides. Okay, and sulfur oxide, SO2 is reducing nature, as reducing nature. Why? Because SO2, the sulfur is +4 state, and it can be oxidized to SO3. So it is oxidized, so it is reducing nature. Okay. Now acid rain. All these NOx or SO3, they are, that they are oxides. Sulfur and nitrogen, that they are non-metal, right? Non-metal. So when they form the oxide, so they are acidic in nature. Like P2O5, P2O5 is also acidic. When P2O5 is dissolving in water, it can form phosphoric acid. Similarly, NO2 or NOx or SOx, they also, when dissolved, they form the acid. So if you produce, or industry, mainly industries are the sources of these types of toxic gases. So when they are produced in a larger quantities, then they go to the atmosphere and then they dissolve in water, rain, say for example, and they form the acids, nitric acid, sulfuric acid, okay, and then they again come back to the earth, okay, then they have lot of effects. What are the effects? Okay, what are the effects? These are the effects. They can damage, they can reduce the fish population in lakes, they can damage the forests, they can give rise to corrosion of the metals and erosion of stone and marble structures. Okay, that acid rain, due to acid rain, many marble structures are ruined. Okay, this is all these are the effects, but this effect marble, that from your school also, right? Now there are other sources also. Here it is written: metal, large scale of emission of sulfur oxides from burning coal, metal smelting, however, has altered the atmospheric balance and increased the acidity of rainfall. You will be amazed to see that composition of rain means acid rain. Okay. Now before going to that, I will show you this, the acid rain. You see that from long distance, the SOx or NOx is produced here in this industry, but this area does not get this acid rain. Maybe it goes to a distant place and it can bring the acid rain here. Okay, there are nice examples. In the USA, there is lot of industries and they produce the SOX, NOx, and the acid rain occurs in Canada. Okay, so from US to Canada, far away off. So, but it comes there and produces the acid rain. Okay, same is true for UK. UK, you see that there are a lot of industries, so they produce those types of acidic gases, and then Sweden gets the effect. And Sweden gets the acid rain. So they are far away, but it happens. Okay, it is. I'm not telling stories. It happens. Okay. Now here you can see that the typical acid rain composition. You can see the pH may go to 4 even, so it is too much acidic. Okay, now there are other components, say for example ammonium ion, calcium 2 plus, sodium, magnesium, potassium. Okay, and anions like sulfate, nitrate, chloride, all those. So this is the composition of the typical acid rain. Main interesting part is this one, this pH, very low. Okay. Now, so you have understood that the reducing smog, it is basically smoke and fog, but what is there inside, it is the SOX. Okay, SOX, mainly SOX, reducing smog, and it is whitish in color because SO2 has no color, right? So it is SO, and it is also called London smog. But now I will tell you what is photochemical smog. I told you that for photochemical smog formation, we need four things. One is the sunlight, bright sunlight. Another is the hydrocarbon that is mainly coming from the vehicles. You know, vehicles, when we use the gasoline, it is nothing but the hydrocarbon, but due to incomplete combustion, some of the hydrocarbons, they are escaped. Okay, so hydrocarbons, then some NOx, nitrogen oxide should be there, and ozone. So let us see how it is formed. Okay, so let us start from here. Okay, here. So reactive hydrocarbon, ozone is present. I told you it is another component of photochemical smog. So ozone is there. Ozone is very reactive, so it can form the free radical from the hydrocarbon. Then oxygen is everywhere. Oxygen is there, so this forms another free radical. These are all free radicals because this is unpaired electron. Okay, so this is formed. Then NO. NO means nitric oxide. Nitric oxide reacts with this one and forms the NO2. Okay, NO2 is brown. Okay, NO2 is brown in color. That is why photochemical smog is brown in color, brown haze. Okay. Now this NO2 is formed, then this again reacts with the oxygen to form another free radical, and then aldehyde. It is a stable aldehyde. So aldehyde is another product. Now again NO comes into picture, and then NO2, NO2, again brown NO2 gas is produced. So here one molecule is produced, here one molecule, and hydroxyl radical. Then this hydroxyl radical is very reactive, so it reacts again with the some hydrocarbon, and then it again forms the free radical. So this is a cyclic process. You can see here many molecules of NO2 is produced here, and it is decomposing the the hydrocarbon through this cyclic process, and in between some aldehyde is produced. Okay, so this is the reaction cycle. Okay, for the smog formation. Here it should be written photochemical smog formation. Okay, this is not reducing smog, this is photochemical smog, and you have understood why it is brown. Now this RCHO means aldehyde can react with the hydroxyl radical through different steps, and finally it can produce the PAN. I told you PAN is also a component for the photochemical smog, peroxyacyl nitrate, peroxyacyl nitrate. This is radical, but here the final compound is nitrate. Okay? Peroxyacyl nitrate. That is why the name is PAN. Peroxyacyl, this is L, peroxyacyl nitrate. Okay, this is very dangerous substance. This is very much irritating. Okay, if you pass through this type of smoke, then your lungs, will get damaged. Okay. Now I will show you two pictures, but I will not explain to you. It is your duty to explain. Okay, because you have already understood the smog formation. Okay, and this in Los Angeles, because I told you it is LA smog. Okay, it is named as LA smog. So there in Los Angeles, one study was done, how to know the concentration of hydrocarbon, then NO2 and NO in the troposphere. And it is observed that it is the time between 4 a.m. morning to 8 p.m., even maybe 10 p.m. Okay, so how is the profile, how is the curve? Okay, you have to explain. But why in the morning, around 8 a.m., why hydrocarbon is showing the peak? It is the maximum amount, okay, and then it is going down. And now why the NO and NO2 is showing this type of profile, and this oxidant means PAN. Okay, you have to explain this curve. Okay, if you can explain, then I will know that okay, you understood the chemistry of photochemical smoke formation. There is another, this is a similar thing, but here the NO, NO2 and and ozone, these three components were measured. Okay, and it is plotted, the concentrations are plotted. Why in the early morning you see NO is maximum, and then NO2 starts generated, NO is going down, then ozone is starting generated. Why at here, after the evening, why still NO2 is there, but O3 has gone down, NO has also gone down little bit here. But why it is so? Why? That you have to explain. Okay. If you cannot explain, then I can help. Now here, it is something different. It is the ozone. It is the, you see here, the altitude. It is, you know that up to 11 it is troposphere, and 11 to 50 it is the stratosphere, right? So here you can see that ozone, the concentration of ozone is highest here. That is why in the ozone is maximum concentrated in stratosphere. That you can easily know from the curve. Okay. Now I will tell you something now about the aerosol. Aerosol. What is aerosol? Okay. So there I told about some gases. NOx is also a gas. Then SOx also gas. The ozone, it is also gas. But there are other things also that is called aerosol. Okay, what is aerosol? There are some solid and liquid particles as well. Okay, these are known as aerosols, solid and liquid particles, and their sizes vary from micrometers to millimeters. They can be big also, they can be little smaller also. So what will come under this aerosol? Sea salt. If you go by the side of a sea, you will see lot of salt is coming with the water droplet. Some salt is coming in the form of very fine particles. Okay, so sea salt, dust, and volcanic emission. When there is volcanic emission, lot of particles are coming out. These are all natural sources. Okay, so they all form aerosol. Aerosols alter the Earth's radiative process. Aerosol has a lot of effect on different things. Okay, say for example on the temperature and climate. It has a lot of effect on the temperature and climate. Okay, and a very important component of the aerosol is black carbon, BC. It is called BC, black carbon. It is the soot material. It is also called soot. Okay, that is released from burning the fossil fuels and biomass. Now sometimes in Delhi also you see that lot of this type of black carbons are there. So pollution, lot of pollution is happening because of the burning of the this biomass. Okay, from distant place also, if the wind is in that way, then it may come to other place also. So this is the source. Burning of fossil fuels and biomass. Okay, so aerosol has lot of effect. I'll show you later, maybe in other PPT it is there. Here it is just told that what is aerosol. Okay, now about the size. If you want to know the size, you see that size ranges of particles in the atmosphere. Here these are gaseous molecules. Okay, 10 to the minus 3. Okay, it is in micrometer. Particle size in micrometer. So 10 to the minus 3. Below this is the gaseous molecules. Then here, it is the cigarette smoke. Okay, cigarette smoke. This from this to this, cigarette smoke. Then this is carbon black, BC. Black carbon, BC. Okay. Then sea salt also in this range. Then here it is virus. Then here it is bacteria. Okay. Then here it is pollens. Okay. And this is the fungus. Okay. Fungus. So these are the different size range. Okay. And here it is dust and fungus. There are two things together. Here one stroke is slash is there. One is the dust and this is the fungus. So this is the range, dust and fungus. So you can have some idea that okay, these will come also under this, may contribute to the aerosol. Okay. Now, so I will go to my next lecture. Okay, so up to this, if you have any question, then you can ask. But obviously, you solve these three problems. Okay, these three problems I have shown. Why you have to explain? Not three actually, two I have given. This one and this one. If you just think, then you can easily explain to it. Okay, I will not tell you. You have to explain. Now I will come to my next lecture. Next lecture I will come. But before that, if you have any question in the previous lecture, you can ask me. Okay. Okay, so this next lecture, Hello. Hello.
Yes, ma'am.
There was some problem, net problem. I do not know what happened. Okay, that is why it was not connected. Anyway, so if you have any question for the last lecture, then you can ask. Otherwise, I will go to my next lecture. Okay.